Hello, I'd like to welcome you all to this video lesson on sinusoidal steady state analysis with AC. Now, I just want to mention that the last time if you remember, there's a lecture I gave you on using complex numbers to analyze on how to work with complex numbers. Now, if you watch that video, we took a bit of some time to look at the complex numbers. And the reason we did so was to help us tackle questions that deal with sinusoidal steady state analysis. Now, you need to watch that video on complex numbers to help us understand this document. So now we can try to make some progress and see what we're going to look at in this lesson. Now, guys, I'm asking if you have this document with you. I'm just helping you to understand things to do with complex numbers. Now, what are the objectives of this lesson? So the objective of this lesson, so the first one, we're going to look at the introduction. We're going to look at the converting sinusoidal voltages into polar form. Now, this is very critical right here because in sinusoidal steady state analysis, what we are saying, we are changing the circuit given into its steady state format. Okay, and one of the most important principles is how do we convert a sinusoidal voltage into the polar form or into the complex format. Now this I'll take a bit of some time to help you understand why. And I'll also give you a bit of some background to help you understand why should we go to this length to try to get everything into complex format. Now, if you check the video that I gave you, I took a bit of some time to explain why complex numbers have been a neat way to analyze and to calculate AC circuits. Now we can also look at converting of phasor to sinusoidal voltages, meaning that now when we say phasor, what we just simply mean here is we're converting the phasor, we're converting the polar form, because the polar form has got the phasor angle and it has got also the magnitude. So when we say polar form, it's a number that may look something like this, and maybe something like this. So this is the magnitude, and this is actually the angle at which that magnitude is at. So, and then if we were to plot that on an x or y plane, maybe we can say that this is something that may be lying in the negative, right? So this could be the magnitude arrow, and we could have an angle of -10, something like that. Okay, so now don't worry about these guys, but if you check the video on complex numbers, now I do emphasize that if you fully have to understand this lesson, you have to revise the video that I sent you on complex numbers, because I took a bit of some time to explain. So this one is a link to actually that video. Now we're going to also apply Ohm's law, voltage and current divider rule in sinusoidal steady state analysis. This is what we're going to do. So we're also going to now mesh analysis. We shall not look at this. We shall also not look at sinusoidal superposition theorem for now. We shall not look at the Thevenin's and Norton equivalent circuit, because this is a component due to time I never got to teach you. But I want to mention that so far what you have knowledge of Ohm's law, the current and voltage divider rule, and maybe you also have knowledge of Kirchhoff's laws. So from objective number 1 to 5, this you should be able to look at and try to see how, for example, how do we apply Ohm's law in AC circuits and with respect to complex numbers. Now this is very important. Okay, so let's try to see if we can make some progress here. Okay, so I'm going to just place it in full screen mode, and let's see if we can make a bit of some progress. Now, I want to mention that I'm going to use I'm going to use for the calculations and analysis of the circuits, especially for calculations. I'll try to help you. I'll use for this lesson. I'll try to do the calculations using a software called MathCAD. This is a software I haven't taught you because you don't need to. You have your calculator. You can use your own calculator to do the calculations. Now, after this video, I'll try by all means to help you understand AC. So I will be looking at multisim and trying to simulate AC circuits. So this is going to come after this video. But suffice to say that this is very enough for you right now. You can, but the video lessons on simulations will be just to help reinforce the understanding. Okay, so in the introduction, what we're trying to target and what we're trying to look at is we're going to just try to see this. So now, how do we now having an AC circuit? Now I'm going to give you a rationale behind all of this. Now, if you see in my the video that I sent you on complex numbers, I did mention that if you check it very well, and the introduction to AC is something that I'll also I've got some more follow-ups to make on as well. But don't worry about this because this one is coming at a time when I'm analyzing sinusoidal state analysis. Now, I want to just maybe try to recap and to just try to help you. If you look at, let's just say that we have a circuit right here, right? Let's say I have an inductor, I have the capacitor, and then I have a resistor. We're looking at an RLC circuit, just where everything is there, right? So this is an inductor. All right, now an inductor is measured in Henry. And so let's say that this is a 0.2 Henry. Now you do have an example like this that I gave you again when I was analyzing the complex numbers, and I was just trying to help drive a point home. Why do you need complex numbers, right? Why do we need complex numbers? But just try to maybe just recap a little bit. You see here, this is, let's say we have 0.2 microfarad. And this is, maybe they say this is maybe 2 ohms, right? Things like that. And then you have got a supply voltage. Now, supply voltage in this case can be given in form of the RMS value. So say, for example, we have 120 volts, and then we can say that this is 50 hertz, right? Now, guys, if we ask you a question to try to find what is the voltage across the inductor, so the voltage across the inductor is VL, and what is the voltage across the capacitor, which is VC, and what is the voltage across the resistor, and that is VRR. Now, if you have to calculate this, now we calculate in RMS values. That's the calculations we do. Now, the challenge with this kind of a circuit is that if we have to look at the Kirchhoff's laws, where we can say that the voltage in a closed loop is equal to the supply voltage. In other words, when we want to say if this is 120 volts and Vs, if we say Vs is equal to VL plus VRR plus Vc. Now, these should be in form of a vector. Because why am I saying this should be in form of a vector? So if the supply voltage Vs is equal to the voltage is equal to the addition, because if you look at the DC circuits, that's what we've been talking about. If this is a pure resistive load, if this is 2 ohms, 3 ohms, then we just have to add the voltage across each resistor to be the supply voltage. But now here we've got different values. This may not be the straightforward case, right? So now the way we solve this sort of a circuit in a conventional way, what we do is that if we have to calculate this sort of a circuit, we need to now try to draw, because AC power, everything is found at a certain vector orientation. So we can't just easily add directly. We don't. So, but then what we normally do for us to be able to find the voltages across. Now, you and I, there's no denying the fact that by Ohm's law, if we have to find the voltage across each one of these, first of all, we might need to know the current that is flowing, IS. This is the current that is flowing, right? Now, if we know the current that is flowing, meaning that we can now divide the supply current. If we know the current that is flowing, and the current that is flowing can simply be found by adding the total impedance of the circuit or the total resistance of the circuit divided into the supply voltage, then we know the current. And the current that is flowing through the inductor is going to be nothing but IS times the XL. Okay, meaning that this is the reactance. Now, we did mention about reactance last time in the previous video. Now, we can also find the current, the voltage across the VC is equal to the IS times XC. And the VRR is equal to IS times what? Times the resistor. So these become our voltages, respective voltages. But now, how do we find VC? How do we find IS? IS is equal to this by the total impedance. We have to get what total impedance is. Now, the total resistance of the circuit, this circuit is given as Z, right? Total impedance of the circuit is given as Z. Now, if you check the total resistance of the circuit, again, it's XL. Now, I'm putting it in form of a vector because it also has to be found as a certain magnitude and direction, and plus XC, certain magnitude and direction, plus X plus ZR, which is just directly. Now, you and I would confess and understand that calculating the circuit this way is not a straightforward case, all right? In a sense that now we need to now begin to draw. If we have to do this, we've got to draw some what we call a phasor diagram. Now, a phasor diagram, now I'll just go through this a little bit, guys. So if I have to really calculate a circuit like this, now in my simulation, I'll be able to show you what it really means to get the results for VL, for VC, and for VRM, what it means, because it's not just as directly as you think. So for us to be able to adequately address the challenges of this circuit, if we didn't know the concept of complex numbers, it means that we need to draw our phasor diagrams to really check the orientation and then add appropriately. We just can't add directly things. We just can't add XL plus XC plus VR. So for example, how do we write the phasor diagram of such a circuit? So the first thing you do is that you draw the X or Y plane. So what you do with the X or Y plane, you find that the current, if this is the current that is common, this is common current, right? So we can draw a phasor diagram in this direction. So if we take current as our common, so I'll take this one as my IS to be on the X-axis, then I will now begin to think, if current is used as a reference phasor, as a reference vector, then now we will want to see if this current is flowing in the circuit, when it reaches the inductor here, it will cause a voltage VL. Now this voltage VL, if we check what is the relationship between this current and the voltage that it causes, we know that in an inductive circuit, the voltage leads the current by 90 degrees. So we're going to put the voltage vector for the inductor we shall say VL shall be here because the difference here is exactly 90 degrees. So we can see here that VL will be in this orientation. Now guys, the reason why I'm explaining all of this, and I think, let me just march out of here, then I'll come to the steps that we need to analyze the circuit in sinusoidal form. So let's just go to the board, for example. We're looking at a circuit like this one, where there's an inductor, where there's a capacitor, and where there's a resistor, right? What I'm saying is that without using complex numbers, it is very difficult to analyze a circuit like this one. Of course, maybe it's for a circuit like this one, it's not as difficult. I'll show you why. But then the concept of complex numbers have simplified the way we analyze things. So in complex numbers, we don't have to think too much. We just convert the circuit into its complex format and then solve directly as if we are solving a DC circuit. That's exactly what we do. But we have to solve it the ordinary way, where we have to find VL, VR, VC, and VR, right? If we have to do it directly, this sort of a circuit becomes a bit, we have to draw our phasor diagram. It's the only way we can accurately solve it. So now I'm showing you, for example, without complex numbers, how would you solve such a circuit? Of course, you'd want to draw, first of all, the vectors. So for example, we have to look at our current is our reference phasor. So we can put our current here as IS on the x-axis. And then we say if current goes through the inductor, what happens? If current goes through the inductor, the voltage across the inductor leads the current by 90 degrees. So this becomes our VL. Father, we bless your name. So we see here that if this is the IS, then voltage leads the current by 90 degrees. So in form of a vector, the voltage across the inductor is in the 90 degrees orientation. So now this current will come it will pass through the capacitor. Now when it goes through the capacitor, what happens? The current leads the voltage VC in the capacitor by 90 degrees. So we know that if it is leading, then it means our voltage orientation on the capacitor has to be down. Because the only way you can explain leading, this is ahead and our voltage is facing down from the capacitor. So this on top leads down, the current itself leads the voltage. Now when we talk about VR, when the current passes through the resistor, it will cause VR, but VR is in the same direction as the current, because in a resistive circuit, current and voltage are in the same direction. So now you can see here that there's a vector orientation on top for VC and there's a vector on top for VL. There's a vector orientation down here which is called VC, and along this there is what we call VRR. Now how do we add things like this? So we can't just say directly that VS is equal to VL plus VC plus VR. We can't. So that we have what we call the Ohm's law in a loop. The voltage supply is equal to the summation of VL plus VC plus VR, just by the Kirchhoff's voltage law. We can't do that. The reason why we are using these vectors is to show you. You can even see that the VL is pointing north. This one is pointing south. This one is pointing this direction, right? Things are not as straightforward as we think. So if we were to add this sort of setup, these vectors, then the way we would do, this is how we would do it, we would say that, all right, let's redraw it, we would have to take into consideration. So you and I now are convinced that this is where our VR lies. This is where our VL lies. And this is where our VC lies. How do we add things like this? How do we add? So the only way we can add here is to take into consideration the vectors. So you can see here, what we can do is that if the length of VL is greater than the length of VC, the length of VL is greater than the length of VC, what we do is that we can now find the net effect of the vector. Now, what is the net effect? In this case, we can say VL minus VC. So we have to find the resultant vector. So the resultant vector in this direction, it's the voltage across the inductor minus the voltage across the capacitor. It's going to be VL minus VC. We subtract. So the vector is going to be in this direction. And then now we extrapolate the line of the vector. And we bring it down. So what we see here essentially is that we see here that this is VRR. Now the reference vector here is VL minus VC. And now we can have this angle right here. So now we have something like this. This is VRR. This is VL minus VC. And this is a vector. Now, the resultant vector is what is our supply voltage. That's the mother now here. So how do we now find what is the total voltage? What is the supply voltage equal to? Now, our supply voltage in this case shall be equal to Vs. You know, this is Pythagoras theorem. If you look at Pythagoras theorem where you say that this is a right angle triangle, what we say here is that the Vs is equal to, if you use Pythagoras theorem, Vs is equal to the square root of VRR squared plus now VL minus VC. Like this. It will be like this. That's how you find the total supply voltage. You find it by way of adding the square root of VRR plus VL minus VC. Right. Now, if you look at this sort of a triangle, this is called a voltage triangle. Okay, it's called a what? The voltage triangle. Now, if we check here again, just to help us, now I'm going through all of this just to show you how complex it is to deal with the circuit in its normal form. So now we've said that there is a voltage triangle right here. And in here it's Vs, in here it's like VL minus VC. That is assuming that VL is greater than VC. So there's VR right here. We can actually convert this. If you look at this, we can do this. We can say that our Vs, which is equal to the square root of VRR squared plus VL minus VC, thank you, squared, we can write it in its expanded form so that we have, so what I mean by extended format is that if I know the current, which is IS, if I look at this circuit right here, current times the total resistance of this circuit gives us also the supply voltage. Remember, by Ohm's law, if we say that by Ohm's law, if we say that voltage S divided by the total resistance of the circuit, R total, gives us our what? Supply current. But the R total of the AC circuit is not called R total, it's called Z total. So if we have Vs over Z total, this one is the one that gives us the supply current. So another way we can write Vs, we can write it in terms of IS times what? Z total. All right. So now I'm replacing this Vs, I'm replacing it with I supply Z total is equal to now the square root. Now, what is VRI in terms of IS? VRI in terms of IS is equal to IS times the resistor, right? But now notice that I'm squaring this. Everything is being squared. This is how else I can write VRI. Supply current times resistance squared. Plus, now I can get what is VS. VL, you can see VL is equal to what? VL is equal to the supply current times XL. But then now this one, oh sorry, but then now we can say that minus also IS times what? Times XC, okay, squared. Now, if you have to look at this, we can actually, if you are a mathematician like me, you could actually, it's not difficult to see that such an equation can be simplified. ISZT, if you look at it very critically, if you, for example, let's just do it, we can say that we can factorize out IS. We can have IS squared R squared plus, so what do we do here? We can factorize IS here because it's common. So we can have this equation written as this, XL minus XC squared, but this can also be squared. All right, yeah, so we could do that, and without violating the rules, within this bracket we could actually get our IS squared, and then we can have our R squared plus XL minus XC squared. Okay, now you and I, it's not difficult to see that if this is now our IS ZT. Now, if you further simplify this, it's not difficult to see that from our ISZ, IS squared X squared, we can actually now factorize this one out. We can say our ISZ is equal to IS R squared plus XL minus XC. If we do this, now we can now cancel that and cancel that. So what we have is our Z total now. I wanted to come to the formula for the total resistance. For the total resistance of the circuit, you can also see it's equal to R squared plus, because now the IS and IS can cancel, we can have now our XL minus XC. So now guys, you can even see for yourselves that finding the total impedance of the circuit is not as straightforward, or finding the total resistance of the circuit is not as straightforward. So to find the Z total is not as the way we did it in resistance circuit, where we found the R total. R total for resist circuit in DC circuit, all we did was just to add R1 plus R2 plus R3. But now in an AC circuit, we also need to know, we also have to come from their vector orientations. In other words, we can actually draw what we call the impedance triangle. What we saw there was the voltage triangle. So now we can have our R in this direction, our V our XL in that direction, and we can also have our XC in that direction. So the resultant vector may be one of the vectors in which we have our XL minus XC. And then we can have our RI in here. And this becomes our total impedance as well. So now we can see that the total resistance of the circuit, in this case it's called the impedance. It is also calculated in a Pythagoras theorem where it's not a direct forward thing. Now guys, I just want to show you that so it means that every time, even when I'm given a simple circuit like this one, where I have just an inductor and a resistor, I just can't add them directly, Vs, VL, and VRR. I can't just add these things directly if I'm dealing with AC circuits. I have to draw the phasor diagrams. I have to draw it, know that this is my VRR, this is my VL, and then we have to find the vector orientations to know what Vs is and add appropriately. We just can't say that Vs is equal to VL plus VRR. It's not as direct and as straightforward as you watched this in DC circuits. Okay, so now when it comes now to this document, where is it now? When it comes to this document here, which is our sinusoidal steady state analysis, if we go back a little bit, now it appears to us now that every time I deal with an AC circuit, I have to be careful. If I have to solve it in an ordinary way, I have to watch myself that I don't stumble. I have to make sure that the circuit is in its right phasor diagram. It's like I have to draw a phasor diagram every time I have to do the calculations. I have to draw the phasor orientations. I have to get them right. And so it's not a straightforward case. However, when we deal with complex numbers, I don't have to worry about the vector orientations. All I need to do is that if I have to solve it, I want to solve it exactly as if I'm solving a direct circuit. So what do? So what I should normally do is that I just need to now, what are the steps? So we need, for us to be able to work with this circuit as if we're working with it in DC format, there are some things that we need to do. Okay, we have to convert this circuit in its complex equivalent. And so now there are steps that we do. How do we analyze AC circuits? The first thing is transform the circuit to the phasor frequency domain from the time domain. So now what does it mean? So you may have something like this. Whatever we are seeing here, let's say this is a supply voltage, and mainly the supply voltage may be changing with time in this manner. So we've got to transform the circuit to the phasor, now to the complex format of the circuit. Then solve the problem using simple techniques like mesh analysis. Now I haven't taught you. Now in this case, I'll say Ohm's law. We use now Ohm's law. We can use Kirchhoff's laws. We can use that. And then once the circuit has been converted into complex or phasor form, then now we can transform it back to the time domain where it was. These are the steps that you need to do the calculations. So convert the circuit into the polar or complex format. Now guys, so Complex numbers are a way, in short, of simplifying the circuit and then work with it as if we were working with a DC circuit. Because even the issue of drawing phasor diagram, if we didn't know complex numbers, if the circuit becomes very complex, it's very difficult to draw the phasor diagram. It becomes complex. Now let's just make the some progress. Now let's just look at how do we convert a sinusoidal voltage into a polar format. Now, what I mean by this is this, into its complex format, in short. Suppose I have a supply voltage like Vs. Now, Vs mainly is given as the amplitude voltage, the sine wave, omega t, now plus or minus theta. Now, plus or minus theta. Now, guys, I gave you a document, one of my preamble documents that you have is a document that shows you how the sinusoidal characteristics of the supply voltage, right? So we can say the plus or minus is either a lead angle or a lagging angle. Now you have got all of those things, right? You have them. Now, how do we now change a sinusoidal voltage that looks like this? How do we change it into polar form? This is critical, right? How do we change it into polar form? How do we work with this? Or in short, how do we change into polar form? Now remember, when we talked about complex numbers, we talked about two major forms. There was the rectangular format, rectangular, and then there was an intermediate, which was like a trigonometry format of the complex number. A complex number is something aj plus b, something like this. And then the end, we also had to look at the polar form. Polar form. Now, in the polar form, this is where we have, for example, something like Vm, and then we have plus or minus as the angle, right? So how do we change a sinusoidal format like this into something like that, right? We can directly do that, or we can eventually get into that as well, which is the rectangular format. Now you've got to watch my previous video that I gave you. But real quickly now, let's dive into looking at how do we change the sinusoidal voltage into polar forms. And then we are also looking at how to apply now the Ohm's law and the current divider rule in sinusoidal steady-state analysis. Okay, where is this now? I want to see this. How do we change into polar form? Let me just exit a little bit, because it's like I went ahead without looking at this. Yeah, so now I want to, yeah, this is it. Converting the phasors to sinusoidal, not this one. Sorry about that. Guys, you have this document with you. Oh, all right. Let's just so we'll be working back and forth. So here's the thing that we have. I wanted to make sure. So basically, guys, what we're saying, okay, so now here, don't worry, it's like I feel like I've missed a component here, which is not the one. Is this the one? Oh yes, it is the one. Yes, yeah. So converting phasors to sinusoidal voltages and back and forth, actually this is the following. So here is the point here. This is the point I'm looking at. Now we have our supply voltages, Vs, and even our currents. They are actually in sinusoidal format, right? So here's the point. You have a voltage that looks like this. Look at this. Now this 3677 is the omega part. And what we see, the square root of 250 here is sine omega t minus 35. Now, whenever you are calculating a circuit with a supply voltage, let's say that it has got a V that looks like the root of 2, or it has got a V that looks like this one right here. So if you have to do what we call sinusoidal state analysis, then you have to change this voltage right here. You need to change it into its complex format, or in this case, what we mean by complex format is the polar format of it. Now, how do we convert the polar format of this? First of all, what we see right here is the amplitude value, which is called the Vm. But because mainly calculations are done in RMS values, they can also be done in amplitude values. What we just simply do, we can say that to convert this in polar format, so if we have Vs is equal to Vm sine omega t plus theta, for example, the way we change it to polar format, if we need the results in VRMS format, then this can be converted as you just get the Vm, the amplitude value, and angle. If it is plus, you just put theta, plus theta. You have converted this into polar format. If you want, now this is where you're maintaining Vm as the radius value. But if you want to maintain the radius value as the RMS value, you can also say Vs is Vm divided by root of 2. Remember that if we're converting the amplitude value to the root mean square value, is just the amplitude divided by root of 2, and then we can maintain the angle as that. Okay, now guys, this is not something that is hard, but I just want to keep it simple right here. Look at this. Now what we can get this voltage, so the conversion of this voltage. Now if the result is needed in RMS value but the polar format of it, we can get this amplitude value divided by 2, which is 50. Then we can have an angle minus 35. You maintain, that's how you convert that. Then we can get the current I. We divide it by root of 2. We can get 90.4, and then we maintain the angle 48. That's how you do it. Now, when we talk about the supply voltage, our supply voltage could be that, but notice that mainly we have these as sinusoidal voltages. Now, sometimes the voltage can be given in cosine format, because cosine and sine waves, these are cousins. So we all know that the cosine function leads the sine function by 90 degrees. The cosine function, this cosine function, leads the sine function by 90 degrees. Now, what this means here is that if I have to convert this, if the voltage has been given in form of a cosine function, then what I can do, I can first convert it into its sine format. So for example, if I have V root of 283.6, then cos 400 t minus 15, what I can simply do is that I can convert this very same to the sine function. So what it is that I can have root of 2, 82, 6, then I can have the sine 400 t minus 15 degrees. So now minus 15 degrees, then I can add this. If I add 90 degrees to it, then definitely it converts into the cosine function. Because the way it is, so I write it the way it is, then I add 90, then it means that sine wave, if I add 90 to it, because this one leads the sine function by 90 degrees, then I have converted this one to the sine function. And it's the sine function that can easily give us the phasor or the polar equivalence. Now let's just look at what we mean by this. Okay, so real quickly, you and I can see that, so in short, whenever I want to convert these two which are in cosine format, I'll rewrite them the way they are, but I'll change into their equivalent format by adding a 90 degrees. And if I add, so I'll have something like, since this was minus 15, so minus 15 plus 90, that gives us 75, right? So then it means that I'll just divide by root of 283.6, because I'm working with VRMS values, then I'll say angle 75. Same applies. If I do this again, I'll add the 30 plus 90, then I'll divide this by root of 2, and then I have that. So now whenever I write these in this manner, it means now I'm learning how to convert the supply voltage, I'm learning how to convert it, or supply current, I'm learning how to convert them into their polar format. Now I can say that solution using VRMS values. So we are using the VRMS values to be the angle, to be the amplitude, or to be the scalar part, or the error part, now which we shall discuss as we go on as well, because you have this document, that introduction that talks about that. So now we can also convert the phasor to sinusoidal. Now what does this mean? So what this means, before we dive into there, what this means is that I say that if I have a supply voltage that is Vm, let's say sine omega t plus or minus theta, to convert this into the polar format is, we can say Vs, I'll put the star on top to make sure that, to show you that this is a complex format. Its complex equivalent can be written in terms of VRMS by dividing by the root of 2, which is making sense, and having an angle. Now what is this angle? This is plus or minus what? Theta. This is what it means, plus or minus theta, right? That is the point. Now, can we now address this issue where now if we put it, we can also write it in complex format of the amplitude value. We can say Vm plus or minus theta. We can do that as well. So guys, be comfortable to do all of this, both of them. It's fine. Now the question that comes now is that what if now we have been given something like this? Let's say that we have been given Vs is equal to, we've been given in polar format or in complex format. Now we need to go back to where we came from. So if you've been given this, and then we come, but we need to go back to Vs in time domain like this. How do we do it? So what we just do is we just get this one right here, which is meant to be, because in this case it's the VRMS values we are using. So we can convert back by maintaining, we can say this is Vm, so we give the Vm, and we write the function itself, and then we write whatever omega is. There it's 377, you saw it. Then we can write back as plus or minus theta. It's just that simple. We just need to know the amplitude and the angle. That's all. And the function will just sit in. We slot it in. Okay. Now real quickly, let's make some progress here. We can, now let's go back. We can now do this, and then we can apply Ohm's law, voltage and current divided, and then current. Wait. Okay, so let's just, okay, so now here's the point. Now we're converting the phases, we're converting them back to the sinusoidal voltage. So for example, if we have a voltage that looks like this, how do we take it back to the sine and things like that, right? And if we have that, how do we take back to the sine and things like that? Okay, so here's the point. Okay, so this looks like a repetition from what I did the last time. Looks like a repetition because the voltage here is given as that, and I did mention that the way to do it, it's where we just have to add 90 and then we got that one. And then if we've been given as this, we just add and then we get it as that one. So we can also have things expressed like this. But here is what I'm trying to say. Look at this. I have a supply voltage. Don't worry about these other ones because this is a repetition from the previous case. And I'll have a discussion also on this one. Here's the point, guys. For the supply voltage and currents, this one can be converted V50 volts. If we're working with VRMS values, then you know that if this is a VRMS value, then we need to multiply by the root of 2 to find its amplitude. It's the only way. We know that VM divided by root of 2 is VRMS value. But for us to get the amplitude, we should multiply by the root of 2 VRMS. It's just that simple. Okay? You get it? So let's get it straight here. So we can see for ourselves here that we can multiply 50 times root of 2 and then we just write the sine function. We already knew that this was omega. Omega, by the way, is 2 pi f 377 t minus 370 minus 35 degrees, so we can maintain the minus 35, and that is converted back. And if you look at this one right here as well, it's 90 times root of 2, it's another truth, sine, now 7542. Now 7542 in this case, guys, I didn't just emphasize, I'm saying 7542, these we're working under certain frequencies. Otherwise, let's just try to elaborate on this number as well, because this could be confusing to some. It could be confusing even for me too, because why is 7542 and why is it here 400 and why is it 815? It's because now I have not explained to you how these values are coming about. So for example, the general formula here, we know it should be V sinusoidal, it's Vm sine omega t plus or minus theta. Now, if you look at this omega, it's something that has to do with omega is the 2 times pi times f. So now, depending on the frequency that we are talking about, if the frequency is 60 Hz, then we can multiply 2 times 3.14 times 50. That gives us the equivalence of the omega here. So if in this case, of course, we can say that our omega in this case was 754. So it depends. Now that's omega. So this was our 2 pi f. So the frequency here that was being used was 754 divided by 2 pi. You can see that's the frequency. So that's what led to this one. So now, in other words, the values of this every time you're doing the conversion depends on what frequency was looked at. So don't worry about this because I haven't mentioned the frequency anywhere. So this 377 could mean that frequency was probably 50 hertz, right? If you multiply 2 pi f 2 times pi times 50, that could probably mean that this was about, that could probably mean that this was that. This could be a different frequency and that could be a different frequency. But really here, this is how you do the conversion. You can see right here, right? Now, what about these voltages, right? So now this one is something else again, because if you want to get back to the cosine wave, but you can see here that we are the cosine minus 50, then we convert it back to this. And if this is the case, the way it is, and we have to convert back to the, if we have to convert this back to the sinusoidal, then we can get that, multiply by the root of 2, then say cos, now depending on the type of frequency that was used, we can say 400t. Now, if we have to use the cos, now remember that if this is a cosine function, then we had to add 15. If this was the way it was, right, minus 15, then when we add plus 90, then that's the equivalent of that, right? So if this gives, so we can get first to the sine function, which is normal. We can say, in fact, we can say root of 836. Then we can say sine, all right, 400t plus 75. If we want to go to the, so this can be, okay, so let's just get it. We can say Vs is 83.6 root of 2 sine of what? Sine of omega t, we don't care about that, it's frequency, plus 75. Okay, now if this is a sine function, then it means that in polar form, it's 83 point, okay, so we're getting it the way it is, we're getting it as that, right? We know that the sine function lags, it lags the cosine function by 90 degrees. Okay, so in other words, if it's a sine function the way it is, if we have to take it back to the cosine, then we can just simply subtract 90 in this case. Because we have started with the, we've started with the sine function, so we can subtract 75 minus 90, which gives us minus 15 if we want it to be in cosine function. But remember that the cosine function is something that is also rarely used, especially for our analysis. You won't see it, but this is just to help you understand that definitely if we had it like this in sine format, and if it's needed in cosine format, then definitely you should remember that the sine function lags the cosine function by 90 degrees. Okay, things like that. And we could actually also, in this case, we can convert this, you can see here, converting to sine function. It means the sine function, if you write it the way it is, plus 30, then we add in 90, right? Because that lags. And we can easily convert. So in other words, we can convert between the sine function and the cosine function by this simple understanding. Remember, guys, how the cosine function and the sine function looks like, by a simple understanding that the cosine function leads the sine function by 90 degrees. So these can be converted. So for example, if this is the sine function, then the cosine function will start somewhere here. And you can see it will always lead by this angle. So if I know this, I can easily know that How do I know that? So I get whatever this is, I'll add 90 to be shifted by 90 degrees. That's the understanding. So if I know the cosine function and I want to get the sine function, if I know the sine function and I want to get the cosine, I just need to add plus 90 degrees if I know the sine function. But if I know the cosine function and I want to get the sine function, I can always subtract 90 degrees to get to the sine function. Things like that. That's the understanding. Okay, and it shouldn't be confusing. Okay, so now here, we can make some progress now. Tomorrow, maybe go to the seat, go to mommy. Okay, so now how do we apply Ohm's law? Applying Ohm's law, voltage and current divider rule in the AC circuits. Now, real quickly, guys, I'm going to go through this. Here is a question. You have a circuit, and this circuit, it has got a resistor of 3.6 kilo ohm, and it has got an inductor of 1.2 ohm Henry, and it has got a capacitor of 0.04 microfarad. Okay, now we have a supply voltage that is in this manner. Now, how do we solve this question in a sinusoidal steady-state way? How do we solve it? So the first thing that we've mentioned is that we need to convert the circuit into its polar format. That's what it is. This question, first of all, we convert it into its what? Complex form. Now, the complex form that we're talking about here is simple. If we choose to work with VRMS values, for example, this voltage, as you can see, we have to convert this voltage into its polar format. Now, what is the polar format of this voltage? The polar format of this, it's not difficult to see that this is our VM and this is our angle here, right? So we can choose, if we choose to work with amplitude values, then it's true that this is going to be 140 angle minus 10 degrees. If we choose to work with VRMS values, then it's 140 divided by root of 2 angle what? Minus 10. So you can choose either to work with amplitude values directly like the way it is, or you can choose to work with VRMS where you can first divide the amplitude by 2 and then maintain the angle minus 10. So in this case, let's say, for example, we just want to work with amplitude values, which is in any case not confusing, it's just one and the same thing. So we can convert this one right here. It can become 140 angle minus 10. Now we come to the resistors. So the resistance now also has to be changed into complex format. Now, if you check my previous video, there was a way we were converting the values into complex format. So for example, the resistance will maintain itself as 3.6 kilo ohm, but then we have to convert it into the standard value, which is ohms, which is say 3,600 ohms. What about the inductor, which is about 1.2 Henry? Now remember, for the inductor, we want to mention here that the inductor, if you convert the inductor into its complex format, now when you check my previous video, or even now I can explain that the reactive inductance XL in its complex format, when we have to convert in a complex format, it assumes J, which is the operator, omega L, where L is what? L is the inductance value, which is in this case 1.2. What about omega? Omega, this is the frequency, the angular frequency. Now, where do we get this angular frequency? Well, it's gotten from here, because This is omega t. So omega, in this case, omega is 4,000, because the general formula for the supply voltage is Vs Vm sine omega minus 10 degrees Celsius in this case. So this, therefore, is our omega. This is our 4,000. So in this case, our XL shall be J omega, which is 4,000, times the 1.2. And that will give us the XL, which is the inductive reactance. Now, what about the capacitance? We did mention with the capacitor, we say for the capacitor, we say that XC, which is the inductive reactance, or the capacitive reactance, is minus J divided by what? Omega. So in this case, or omega C, sorry. We have omega and C. So in this case, XC will be 1 divided by, in this case, omega is 4,000, times 0.04 microfarad. Now it has to be in farad, so we should multiply 4 times, in this case, 4 times, or 0.04. We have to multiply, so just a minute. Just a minute, guys. So we can actually say that in this case, we have to convert everything into complex format. So we have XC is minus J divided by omega C. In this case, minus J divided, what's omega? Omega is 4,000. Times, what is C? The C has already been given to be 0.04 times 10 to the power minus 6, because microfarad is actually a factor of minus 6. Okay, now here we can now get everything in perspective, right? So for example, real quickly, what we're saying here is that if we have to work with the circuit and where we have to apply our Ohm's law, voltage and current divider rule in sinusoidal state analysis, then our task is to convert everything in complex format. So everything in complex format means our voltage will be converted either using its amplitude with a minus angle, and that is a polar format. And in here we can maintain, and in here this is going to have J omega, and this one here is going to have minus J over omega what? Omega C. So basically, that's how you work with this sort of a thing. Now, once you do that, you've converted, then you can work with it as if you're working with a DC circuit. Now, real quickly, guys, let me just walk you through the next portion, and then let's just see what we see here, because calculations were already done. So now we can see, guys, now what I've done is exactly what I've told you. So basically now we are converting the phasor form of the circuit. Now phasor form of the circuit, or the complex form of the circuit, we know our supply voltage to be that. Our frequency is that. So if we have to find our J omega, then we can say our XL J omega is J 4,000 times 4,000 times 1.2 Henry. And if we do that, we shall get J, which is 4.8 kilo Henry. Not, in fact, here it's supposed to be a K. I missed, that's a typo. But then now that assumes J 4.8 kilo Henry, 4.8 kilo ohms. XC, you can see our XC is also calculated. So when we say minus J divided by 4,000, which is our frequency, times 0.04 times 10 to the power minus 6, and then we can see that this is minus J, and that is it. So now when you convert the circuit in this manner, what have you done? You have simplified everything. This is beautiful. Now you can see here now what this means here is that you could now calculate the relevant values. So what is it that you're looking for? So if we're looking for current that is flowing in the circuit, for example, if we're looking for IS, then in this case we don't have to draw anymore our vector orientations like the one we did. We don't have to. It's already in complex form. We just have to solve it directly. Babe, go to the bedroom where mommy is. I'll find you. Is it Penny? Okay, I'm coming now. So guys, this is exactly how we do it. Just wait a minute. So here now we can have all of that. I'm coming just now, Deborah. So here, let's just see how we can quickly work it out. Real quickly, we can now get our total resistance of the circuit. Now, what is our total resistance of the circuit? This is coming from our R plus J4800. It's coming from our what? XL minus J6250. It's coming from our what? Our XC. Now we find the total impedance of the circuit. Now, if we find the total impedance of the circuit, we can convert this, because if we're looking for current, current is going to be equal to Vs divided by Zt. So we found our total impedance. You remember when I told you in our previous analysis, I said that it's easier to divide in polar form than in rectangular format. So we can look at, you can check also so if I convert this in polar format, it's going to give me that. Because you need to add and then convert. Use your calculator to find that. Our voltage supply has already been giving us that. So if we have to find the current by Ohm's law, then we're just going to have 140 angle minus 10. Then we're going to divide by our Z total, which is this one. And our current, if you calculate using polar form, you should be able to get the current as that one. 36.1 angle 11.9. All right, this is what we have in polar format. So you can see here we're dividing directly with the full knowledge of what's going on. And if we have to find the voltages across, we just know the current is already known and we multiply by the resistance. So for example, here we know that 36.1 divided by 11.9 times 3600, we get 130 as a voltage. Voltage across the inductor is current times XL, so we just need to get it the way it is, multiply, and then these are the values that we have. If we get this, we can also calculate current times XC. XC is already known. Where is our XC? Our XC is this one. And if we multiply this times the, so since we are multiplying, XC should also be converted into polar format, which you already know from the previous video. I took some time to explain how to convert between polar format and rectangular format, because you are multiplying, you don't want to multiply things in rectangular format. We can only add and subtract in rectangular format, but when it comes to division and multiplication, we multiply in polar format. And this you are able to see. Baby, I'm coming just now, okay, baby? So we can see here that this is exactly what we have in terms of handling this. So real quickly, guys, you have the documents with you. If we want to convert, so knowing their polar formats, for example, I know that my current is in this manner. My current is 36.1 angle 11.9. I can easily convert 36.1 angle 11.9. How do I convert it back? Well, if the current is needed in sinusoidal, remember I worked with the amplitude value, so I don't have to divide by 2. I can say 36 or multiply by 2, sorry. I can say 36 as my amplitude, sine omega t. This is positive plus 11.9. I have converted that back to sine to back to where it was. All I need is just the amplitude and the angle. That's all. So you can see here if this is my IS changing with time. Okay, all right. So we can go back, we can make some progress, we can check now here. This could be the current. The voltage has already also been calculated. If you check what is with the voltage, let me just check it real quickly. Voltage is 130 angle 11.9. So it's 130 sine. Now I'm using 4000 because that was the given frequency. So it's 4000 T 11.9. Let's go to voltage. VC, you can see it's 225 minus 7.8. VC 225, 4000 T minus 7.5. This VL $173,102. 170 sine 40 plus 102. So guys, this is exactly how you get it. And I want you to take your time to digest this document, and we shall have some further analyses where I'll be analyzing a more complex circuit in video number 2. Now, I'd like to really thank you for viewing for now, and we shall meet now in the next class.